Temperature is one of those things that affects us every day, from the moment we wake up to the moment we go to sleep. Whether it's in the shower, with that cold bath that nobody deserves, or when you're drinking your coffee, when it's colder than it should be. But have you ever wondered what exactly the temperature is measuring? And is there a limit to it? Let's dive into this universe of heat and find out. So, let's dive into a question that arouses curiosity. What exactly is temperature? In essence, we can describe it as the average kinetic energy of the particles of matter that make up the universe around us. Whether in a solid, liquid, or gaseous state, these particles are not static. They dance in a constant ballet of agitation, moving and vibrating at different rates within objects. This agitation is what defines a body's temperature. The more intense the dance of these molecules, i.e., the faster they move, the warmer the object becomes. This reality surrounds us in such a fundamental way that it influences everything from the weather to the thermal sensation of our skin. But what if, for a moment, we imagined the hypothetical scenario in which these particles completely stopped moving? This theoretical condition is known as absolute zero, the coldest point imaginable. In numerical terms, reaching absolute zero means reaching 273.15 degrees Celsius or 459.67 degrees Fahrenheit. Reaching this temperature is more than just an impressive mark on the thermometric scale. It represents a state of matter so exotic and unattainable that it challenges our understanding of classical physics, entering the realm of quantum mechanics. At absolute zero, the particles of matter are as immobile as the laws of physics allow, a condition which in itself opens the door to mysteries and wonders in the study of the properties of matter. The mere thought of this extreme condition is enough to send shivers down the spine, sparking the imagination about what beyond our current knowledge the universe still has to reveal. But what about absolute zero? Is that the limit? But that's where it gets interesting. We've already recorded temperatures close to absolute zero, but is there a maximum temperature? When would molecules be moving at the speed of light? It's a tempting idea, but things aren't that simple. Imagine we have in our hands a small sample of the atmospheric gas that is so vital to us, the air we breathe every day. Under normal conditions, at room temperature, the molecules of this gas oscillate in a constant frenzy, moving at dizzying speeds of around 300 meters per second. This frenetic activity is a direct reflection of the ambient temperature we experience on a daily basis. Now suppose we decided to increase the temperature of this sample of gas. As we heat it up, we increase the energy of the molecules, causing them to shake even more vigorously. This in itself is an interesting phenomenon. But then we take our imagination to a far more radical scenario. What would happen if we transported this sample of gas directly into the heart of the sun? On the sun, we're talking about temperatures that are simply staggering, reaching approximately 32,000 degrees Fahrenheit on the surface and much more in the core. Under these extreme conditions, the behavior of the molecules in our atmospheric gas would undergo a radical transformation. The molecules would shake with such intensity that the electrons, which orbit the nucleus of the atoms, would be ripped from their atomic homes and completely released. The result? A turbulent soup of charged particles known as plasma, the most abundant state of matter in the universe, but at the same time one of the least familiar to us. In this solar plasma, the concept of a molecule as we know it no longer exists. Instead, we have a sea of atomic nuclei and free electrons, all interacting with each other in a chaotic ballet of pure energy. This state of matter is so extreme and energized that it plays crucial roles in cosmic processes, from the nuclear fusion reactions that power stars to the aurora borealis that dances in Earth's polar skies. What if we want to get even hotter? Then we need to go further. Stars, more massive than the Sun, for example, reach billions of degrees Fahrenheit in their cores. It's a veritable nuclear fusion factory where atoms are transformed into other elements, and it is from this process that even the heaviest elements on the periodic table, such as gold, come out. Incredible, isn't it? But wait, there's more. When a giant star explodes in a supernova, temperatures reach 18 million degrees Fahrenheit, and even iron, which is resistant to star fusion, melts. All this in an explosion that can even generate new elements. It's like a real cosmic matter factory. And so the question arises that challenges our curiosity. Is there a limit to how hot something can get? The answer is as fascinating as the question itself. In fact, there is a record for the highest temperatures ever reached, and it stands at a staggering 126 quadrillion degrees Fahrenheit. This is not something you would find on an ordinary day, but in the vicinity of formidable cosmic entities, such as the supermassive black holes that reside at the heart of galaxies. At this point, the laws of physics as we know them begin to bend under the weight of extraordinary concepts. When we reach such stratospheric temperatures, we plunge headlong into the depths of general relativity and quantum mechanics, territories where Einstein's famous equation, EAMC2, reigns supreme. This equation is not just a formula, it is a gateway to a universe where energy and matter are two sides of the same coin, capable of transforming each other. Within this cosmic cauldron, particles don't just move or interact, they can literally be created from the available energy. This phenomenon leads us to rethink the very fabric of reality, where the boundaries between what is matter and what is energy become blurred. When we stop to reflect on the maximum temperature that the universe can reach, we enter a territory of pure speculation and wonder. After all, if we simplify temperature to a question of how much energy we can squeeze into a given space, then the theoretical limit would become the compression of all the matter and energy in the universe into the tiniest space imaginable. This reasoning takes us directly to the Big Bang scenario, that colossal event that marks the birth of the universe as we know it. Just imagine, at the beginning of everything, the universe was nothing more than an infinitesimal point, crammed with energy on an incomprehensible scale. At that time, temperatures reached such extreme levels, so absolutely high, that the concept of hot can barely do it justice. In that primordial era, the universe was a furnace of pure energy, where conditions were so intense that the laws of physics, as we understand them today, had no applicability. It is difficult to even begin to imagine the magnitude of these temperatures, as they existed in a state of the cosmos where time, space, and matter merged in ways that defy our comprehension. In essence, the temperatures were so high that the basic components of the universe, the elementary particles and the fundamental forces, were all mixed together in a primordial soup with no clear distinction between them. This reflection on the maximum possible temperature leads us to appreciate the incredible journey of the universe from this state of extreme heat and density to the cold, structured vastness we observe today. It's a journey through time that spans billions of years, from the initial instant of expansion and cooling through the formation of the first elementary particles to the fusion of matter that eventually formed stars, galaxies, and everything else that exists. By pondering these concepts, we not only explore the limits of physics and human knowledge, but also connect with the singular moment that gave rise to every particle, every star, and even ourselves. It shows us that all the elements of the universe are interconnected, sharing a common origin in that cosmic cauldron of pure energy. So the limit of maximum temperature is not just a number, it's the limit of our own knowledge. Maybe one day, with new discoveries and theories, we'll be able to explore this fascinating world of extreme heat even further. Until then, it's best to turn on the air conditioning if the temperature rises too high, or maybe we'll even create some new particles in the room.